Subnetting is one of those things that people try to avoid, but we're going to try to make it as painless as possible. We're going to talk about why we subnet, subnetting in binary, breaking the IP address down in binary. It's a pain, but it works, and you can see what's going on with the numbers. And then we're going to do a few practice questions. We're also going to talk about CIDR and supernetting, what that is, variable length subnet masks, and how we implement that in our network. And there's also a couple of references I want to point out. Learn2subnet.com. It's a website that's got a bunch of videos. It's got some practice questions for you, as well as subnettingquestions.com. Subnettingquestions.com basically generates one random subnetting question after another for you to practice. So once you're done with this video, you're going to have to go in and practice. Practice is what's going to get you to understand subnetting thoroughly and feel comfortable with it. And this is a very important topic because understanding IP allows you to understand the network more completely, as well as understanding all the layer 1 cabling. IP addressing and subnetting is extremely important, so you're going to have to practice once you get done with this video. So let's take a look at a sample network and why we might need to subnet. Now, subnetting allows us to take one network address. If we just have one network address, 12.0.0.0, let's say we just had this one network address. We could only address one broadcast domain with this network address out of the box with a /8 subnet mask, also known as 255.0.0.0. /8 simply means turn the first 8 bits on, which gives us 255. All the other bits are off, so that's our subnet mask. So with this, we can only address one broadcast domain. Let's take a look at why that is. I'm going to draw in some computers over here, and this subnet over here, represents a subnet right here, that sideways T. Let's say there's a couple of computers right here. This guy's IP address is 12.0.0.1. This is 12.0.0.2. The subnet mask they're both using is 255.0.0.0. The way computers communicate with each other, let's say I want this machine right here to ping this machine. How they do that is when I type ping and then the IP address of 12.0.0.2, the computer compares the destination IP address to the subnet mask. And what happens is he moves all the zeros up, does this process called ANDing, and he gets what's called the network or subnet address. And so when he does that for this 12.0.0.2 address, he sees, okay, that's network 12.0.0.0. He compares this network to his own, and he does the same thing to himself. He's like, oh, that's network 12.0.0.0. So in that situation, when the destination node is on the same network, the machine ARPs. ARP sends out an ARP. It says, hey, 12.0.0.0 or 12.0.0.2, I need your MAC address. And his MAC address might be AB. He sends it back over. Hey, my MAC address is AB. And then he takes the MAC address, packages the information, puts the MAC address on there, sends it out. If we didn't subnet, so everybody was using a 12 address, and this router might be in a completely different part of the world. We have a WAN connection here, and he's in a subnet over here, and we didn't change anything, and we give this guy an IP address of 12.0.0.3. And he wanted to communicate with 12.0.0.1 all the way over here. So what's he going to do? We type in ping 12.0.0.1. This guy goes, okay, 12.0.0.1. Let me compare that to the subnet mask, 255.0.0.0. And he goes, okay, that is network 12. And then does the same thing for himself, and he goes, oh, I've got network 12 as well. So what's he going to do? He's going to send out ARP. So he ARPs. ARP is a broadcast message and does not go beyond the router. ARP is destined for everyone in the same broadcast domain, and it can't pass through the router. This guy over here never gets the ARP, so he's never able to send his MAC address back over. So this guy cannot communicate, because instead of trying to ARP this machine, what he should be doing is ARPing his default gateway and sending the message to the default gateway to get there. But if this network is a network 12.0.0 and it's not subnetted, then the devices can't communicate. So let's look at actually having the network subnetted a little bit before we do some subnetting and show you how the process is going to work when it's actually subnetted. I cleaned up the slide, and now we're going to look at those same two computers. This guy over here, this guy over here. They're talking to each other. And have a system all the way over in the corner here. Now, there are 9 different broadcast domains in this scenario. 1, 2, 3. Did I say 9? I counted 4 additional routers instead of 5 over here. So 6 routers altogether. 11 broadcast domains. I can count very well here. Every connection, the router basically separates broadcast domains. So on this side of the router is one broadcast domain. Between the routers is a shared broadcast domain. And on the other side of the router here is another broadcast domain. So what I can do is I can take this 12.0.0.0 address, and I'm just going to use a different subnet mask, 255.255.0.0. And I have subnetted this. I'm not going to go to the process of this one. We're going to go in more detail in a moment. But basically what I've done is I've said this entire octet right here, where this first 0 is also part of the network address. So now we've got a bunch of different subnets. Over here is subnet 12.1.0.0, and what these guys are on is subnet 12.10.0.0. The new subnet mask is /16 instead of /8. So let's take a look at what happens now when this guy wants to communicate with this guy. Let's say his IP address is 12.10.0.1 and this IP is 12.10.0.2. So he does the same thing. He communicates. He wants to. I type in ping 12.10.0.2, and he goes, okay, 12.10.0.2. Let me compare that to the subnet mask. And he goes, okay, your subnet is 12.10.0.0. That's the same subnet I'm on. So what's it going to do? ARP. ARP's out. This guy replies to the ARP, gives them the MAC address, and they can communicate. But what happens when this guy over here wants to ping router 12.10.0.2 now? He's going to go, I type in ping 12.10.0.2, and he does the comparison thing. And he goes, okay, 12.10.0.2, compares it to the subnet mask. And he goes, whoa, you're on subnet 12.10.0.0. My subnet is 12.1.0.0. That means I've got to go through my router to get there. So that's a big thing right there, whether the router is going to be able to communicate locally or remotely. He recognizes that the subnet is not local to his. So he's on 12.1, this guy's 12.10. The only thing he needs to do is ARP his gateway. So instead of getting the MAC address for this machine right here, he's going to get the MAC address for his default gateway, which might be A1. And he goes ARP, gets his gateway's address, the gateway sends him his MAC address, and he sends the package through the switch to the default gateway. The default gateway takes it from there and goes, oh, I'll send it over to this router, and that router takes it from there and sends it to this machine. So it's very important that we have subnetting to make more efficient use of our IP addresses, as well as to allow the computers to communicate. If we didn't have subnets, we'd have to have a lot more network addresses to be able to address every one of these individual broadcast domains. So let's take a look at the process of subnetting. I've cleaned up this slide yet again. So now we're going to take a look at the subnets. We've got one subnet there, or one broadcast domain. 3, 4. Let's see if I can get it right this time. There's 11 of them. 6, 7, 8, 9, 10, and 11. Now, we want to address it. We're going to be using the 12 network address /8. Now, it's important to know a couple of things. I'm going to jump back here real quick. It's important to understand what class of IP address this is. This is a class A IP address. So let's take a look at a couple of these things before we go in and subnet this out. I've brought up the slide real quick of network class boundaries, and this is just something that you have to know. If it's a Class A network address defaults to a subnet mask of 255.0.0.0. So what that means is there are a limited number of Class A addresses, since only the first octet is part of the network address. And we know that because of this subnet mask right here. It's very important to understand something, that the subnet mask is a tool. It is a tool to allow us to tell where the network portion of an IP address ends and where the node portion of the IP address begins. It's kind of like allowing the postal carrier to tell the difference between the zip code and the street address. What this tool does, and this tool can be manipulated, is it tells our computers, like this tool right here, tells the computers that, hey, left side of this line is network address, right side of this line is node address. Since the Class A networks have a 255.0.0.0, only the first octet is part of the network address, and only numbers 1 through 126 are part of the network address. So we've got 126 basically Class A network addresses. 127 is reserved for loopback. If you're ping 127.0.0.1, you get a reply. It tells you that TCP/IP protocol stack is installed appropriately on your system. It doesn't tell you that physically your NIC is working and your cabling, all that, but it tells you that TCP/IP is installed appropriately on your system. So if the number is between 1 and 126, we know that that is a Class A address. If the number is between 128 and 191, it's a Class B. But check out the subnet mask for a Class B, 255.255. So if we have a Class B, we've got a bunch more combinations of zeros and ones. First of all, I have all the options in the first octet of 128 to 191, and then for each one of those options in the first octet, I've got an option of 1 through 255 in the second octet, because this subnet mask says, hey, not only is the first octet part of the network address, the second octet is also part of the network address. Now, the Class C has 255.255.255.0. That has 3 octets. There's 16,777,000 plus network addresses with Class C, because not only do you have 192 to 223 in the first octet, you've got 1 through 255 combinations and another 1 through 255 combinations in the second and third octets. The only problem with the Class C is you're more limited to the number of nodes per network. You're limited to 1 through 254 in the node portion of the address. It gives you 254 node addresses, because 255 is used for broadcast. So you're more limited on the number of node addresses you get, but there are a ton of Class C network addresses out there. The last two, 224 through 239, multicasting, which is a multicast is an IP or a broad type of broadcast. It's not necessarily broadcast. Broadcast goes to everybody. A multicast goes to a group of nodes that are listening for messages on a particular multicast address. Like OSPF. When a router sends out its OSPF updates, he sends them to to the multicast address of 224.0.0.5, and all the other routers are listening for those multicast updates on 224.0.0.5. It's a good example of a multicast address in use. Class E is used for research, that's 240 and above. So those are the basic class boundaries, and you should be comfortable with these because that's going to tell us something. Because if I have a 12 here, and I'm using this subnet mask, that means I've got a whole bunch of subnets. I've got, I think it's 65,000 plus subnets I've got here. If I'm using a Class C network address, like say 201, and I'm using the same subnet mask, I don't have any subnets because a Class C uses the first 3 octets for network portion. Class A only uses the first octet for network, so that way when I use a Class C address, I get 2 octets of subnets. Class C address, I don't get any subnets out of this mask because this is the default mask. That's my starting point. So it's very important to be able to look at the first number in an address and be able to determine what class it's a part of, because that tells you what the starting point was for the subnet mask and how many potential subnets you have based on the new subnet mask. Let's go back to that subnetting that we were doing. We're actually going to subnet something. So here we were in a network with 11, all the way up to 11 subnets. We're using the network address 12.0.0.0, which is a Class A, which is /8 or 255.0.0.0. And what I'm going to need to do with this subnet mask is I'm going to need to change it because with the 12 the way it is, I can only address one of these broadcast domains. So what I have to do is I have to use some of this area over here to represent the sub portions of network 12. So it's basically like this whole thing right here is network 12. Let me draw a big circle around it. So this whole thing is network 12, and then we've got sub areas of network 12. So sub area 1, 2, 3, 4, and so on. So we're going to use our tool, which is the subnet mask, and manipulate it to allow enough combinations of zeros and ones to represent these different 11 areas. Let's take a look at an example. I've brought up my slide here, and I don't need 9 subnets, I need 11 subnets. So I've got network 12.0.0.0. I need 11 subnets. Now right now, the subnet mask is right here, and it tells the computer that the network portion is to the left of the line and the node portion is to the right of the line. So what I need to do is I need to take some of this area over here and mark it off as part of the subnet portion of the network. So how do I do that? I change the subnet mask. Now there is an equation that you can use. 2 to the n minus 2 is greater than or equal to 11 is what we're after. This is the number of subnets we need. And I'll explain the rest of this equation right now. Now, 2 to the n. What is that? All that is how many binary spaces does it take to get a certain number of combinations of zeros and ones. If I have one binary space, I have a 0 or a 1 possibilities, which is 2 combinations of zeros and ones. That's where this 2 comes from. The more 2's I have, the more it increases exponentially. Let's take a look at that. If I have 2 binary spaces, which is 2 times 2, 0, 0, 0, 1, 1, 0, 1, 1. I get a total of 1, 2, 3, 4 combinations of zeros and ones, which is 2 times 2. If I have 3 binary spaces, that's 2 times 2 times 2, which is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. That's 8 combinations. So you can see it works. So every binary space, I just multiply another 2 together. So what I have to figure out is how many binary spaces do I need to get 11 combinations of zeros and ones, because each different combination is a different subnet. So all I do to figure this out is I go 2 times 2 is 4. That's not a big enough number yet. Times 2 is 8. Not a big enough number. Times 2 is 16. Is that bigger than 11? Yes, it is. So it takes 1, 2, 3, 4 binary spaces to get 16 combinations of zeros and ones. So all that tells me to do is change my subnet mask. 1, 2, 3, 4. I add 4 more bits, or turn on 4 more bits to the subnet mask, and now this area is going to be the subnet portion of my address. It's that simple. All I have to do is multiply some 2's together until I get a number larger or equal to the number of needed subnets. Now, the -2 right here. We know the 2 is 1 binary space, 2 combinations. The n is the number of binary spaces, so we've got 2 to the 4. The -2 is, in standard subnetting practice, you don't use all zeros in this portion. You don't use all zeros here or all ones. However, you technically can use all zeros and all ones. But Cisco, for the CCNA test, does not like us to use all zeros and all ones. So it's 2 to the 4 minus 2. So we're not going to use the 0 subnet, it's called, or all ones. And that gives us 14 valid subnets altogether, which is bigger than 11. So we're okay. I've cleaned up my slide again. And again, we don't need the 9 there. We need 11 subnets. So we multiply 2's together. 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's 2 to the 4 we need. So 2 to the 4 minus 2 is equal to 14. So I need to add 4 more bits to my subnet mask. So instead of /8, it becomes /12, also known as 255, and this is 128 plus 64, which is 192, plus 32, which is 224, plus 16, which is 240, 240.0.0. So that's our new subnet mask. Now all I have to do is figure out what my actual first subnet address is going to be, and I do that by turning a bit on. Since I can't use all zeros there, I have to make that a 1. That's my first subnet address. So what is that first subnet address? It's 12 dot, and this 2 to the 0 is, or 2 to the 1, anything to the 0 power is 1, and that's what this binary numbering system starts with. It's base 2. So this value right here in this space is 2 to the 0, which is 1. Then we go 2 to the 1, which is 2, 2 to the 2, which is 4, 2 to the 3, which is 8, 2 to the 4, which is 16. So this value, if it's turned on, is a value of 16. So we've got 12.16, because that's the only one that's turned on in this whole octet here. This octet is blank, and this octet is blank. So 12.16.0.0 is my first subnet, and the subnet mask I'm using is 255.240.0.0. Once I have my first subnet, all I have to do to figure out the next subnet is go in increments of this number right here. So I don't even have to mess around with binary anymore. All I have to do is 12.16 is the first one, so I know plus 16, 12.32.0.0 is the next subnet. And then another 16, 12.48.0.0. Whatever the first subnet number you get, that's the increments the subnets are going to go into, because that's your lowest value in the subnet portion. And we can look at that if I wanted to in binary. 0010 would be the next combination of zeros and ones, and that value is 32. So it's 32.0. and then 1, 1. 32 plus 16 is 48. And then 1, 0, 0, which is the 64 value turned on. 1, 0, 1. 16 added to that, 80. Since 16 again is our lowest value here, and we keep going back to this, it goes from 0 to 1, 0 to 1, keeps turning off and on. What it is it keeps adding 16 every time, and we can simply list out all our subnets. So let's go in and fill in the slide real quick that has all our subnets on it, and we'll take a look at how this turns out. We bring up that slide. So here we are. We've got 11 subnets. We know 12.16 is the first one, so we'll go in and write the subnets down here. Let me clean this slide up. So I clean the slide up, and we know there are 11 subnets, so all I have to do is start here. 12.16.0.0 is the first one. 12.32.0.0 is the second. 12.48, and so on. I'm just going to list the first 4 out. 12.64, and then I'll do one more. 12.80. So we have the subnets, and all I have to do is assign the subnets to particular areas. Now the only place that these subnet addresses actually exist is on paper, because I don't type in the subnet address anywhere. But what I would do is, if this over here was subnet 1, all of the machines in the subnet, including the router interface right here, would have an IP starting with 12.16.0.0. That would be the subnet. The IP would start with the 12.16, or more specifically, all IPs would start with this. Anything else after that is valid. So 12.0.0.1, I could have 1.1.1 here, whatever, but this would be the first 12 bits of all IPs in this subnet. And then I would go, this might be subnet 2. There's only 2 IPs that are going to be in this subnet, but the first 12 bits are going to be 12. Start with that. That's the first 12 bits. There's 8 bits here that make up this 12. So this is really, on paper, the only place that these numbers actually exist, but when I type them into the different areas along with the subnet mask, the machines are able to resolve their IP with the subnet mask and come up with the subnet address. We need to know what IPs we can actually type in though. So I've got 12.16 is a subnet, but what's the complete valid range of IPs for this subnet? Let's go back to the IP slide and take a look at that. Alright, I've cleaned this slide up, and now what we're looking at are the valid range of IPs for the 12.16 subnet. So here's 12.16, 12, this is the 16 value right here turned on, and here's the node portion of that address. So all we have to do for the very first IP is turn this value on right here. So all zeros and a 1 is the very first valid IP. We can't have all zeros in the node portion because that's the actual network address. And we can't have all 1s in the node portion because that's the broadcast. So our first valid IP is 12.16. This octet is 0.0.1. The last valid IP, let's put the subnets here, 12.16.0.0. Next subnet is 12.32.0.0. Last valid IP would be all 1s, and then a 0 in the last binary space. So I'm turning all these 1s on right here. What is that value? Well, it's 12, and this is where a lot of people make a mistake. They want to say 16, but that would only be half of the octet. This entire octet right here we have to add up. So it's, get rid of those, 16 plus 1, 2, 4, and 8, because we have these values right here. So it's 16 plus those. And what it comes out to, the biggest number I can get without hitting the next subnet. If I go 32 or more, that's a different subnet. 31 is the highest number I can go, and that's 16 plus 8 plus 4 plus 2 plus 1. This next octet is 255.254. because it's all ones, then a 0. So my valid range of IPs, 12.16.01 to 12.31.255.254. Let's go fill those in. So if I want to, all I have to do, once I list out the subnets, it's real easy. I go 16.0.1, biggest number I can get without hitting the next subnet. So the biggest number I can get, change the color real quick, 31 is the highest I can go without hitting the next subnet, and then 255.254. So I throw that in there. And this one's 32.0.1. The highest I can go is 47.255.254. Now I like to work this in binary first until you get comfortable with the binary. Then these numbers will make sense. 48.01 to 63.255.254. So anything within this range are IPs that I can specify for the 12.48 subnet. 64.01 to 79.255.254. And for this last one, it'd be 80.0.1 to 95, because 96 would be the next subnet, 255.254. So those are the valid ranges of IPs. So that's subnetting with the binary. Let's do a practice problem. So here's one practice problem that we're going to go over. For each question, we're going to find each of the following. I only have one question, so it's not going to be too tough. So for this one question, we're going to find the new subnet mask, the total number of subnets provided. We need a minimum of 80, but how many are we going to get with this new mask? Because again, it more than likely won't get exactly 80. We're going to list out the first 4 valid subnets and then the valid range of IPs for each one of those subnets. So I've got 150.50.0.0. The first thing I do is I'm going to break this thing into binary. So I don't really need to break the 150 or the 50 into binary, because I know that those numbers cannot change. I know those numbers can't change because this is a Class B network address. The Class B default subnet mask is 255.255, so the first 2 octets are reserved for the network portion of the address. So if I were to change this 150 or 50, I'd be using somebody else's network address. And then all I do is convert and write out the zeros. Kind of a pain, but worth it. I don't worry about filling the zeros down here in the subnet mask because I'm going to be adding some ones to it. Instead of /16, it's going to be something else. So now I just simply start multiplying 2's together until I get a number larger than 80. 4, 8, times 2 is 16, times 2 is 32, times 2 is 64, I'm getting close, times 2 is 128. I go, okay, how many binary spaces does it take to get 128 combinations of zeros and ones? 1, 2, 3, 4, 5, 6, 7 of them. So what that tells me to do is go 1, 2, 3, 4, 5, 6, 7. Add 7 more bits to the subnet mask. The rest are going to be zeros. So here is my subnet portion of the address. Now, my new subnet mask is going to be /23 or 255.255. This is 254.0. And now all I have to do is list out my subnets. My very first subnet. Turn that bit on. What is that? I've got 150.50. And what is this value? This value is 1, this value is 2, so 2.0. Now I know my subnets are going to go in increments of 2, so 150.50.4.0, 150.50.8, I'm sorry, 6. It's real easy for me to add 2's there. .0, let me get rid of that. And then 150.50.8.0. Don't make that mistake. I see a lot of people, and I just made it. You go 2 to 4, which is doubling 2, and then a lot of people will double this number. It's not doubling this number, it's just keep going in increments of 2. 2 plus 2 is 4, 2 plus 2 is 6, 2 plus 2 is 8. Then all I have to do is stay in between the lines here for the valid ranges of IPs. 2.1, the highest number I can go without hitting the next subnet is 3, and then the last octet would be .254. So the valid range of IPs here is 150.50.2.1 to 150.50.3.254, and anything in between is valid as well. 4.1 to 150.50.5.254, and that's for the 4 subnet. For the 6 subnet, it's 6.1 to 7.254. And for this subnet, the last one, 8 subnet, is 8.1 to 9.254, because 150.50.10.0 is the next subnet. And that's subnetting. Not too difficult, but it does take a lot of practice. I've brought up this slide on CIDR. Since we went over a subnetting problem, we've got to talk about what classless interdomain routing is. Classless interdomain routing, also known as supernetting. All this is kind of like the opposite of subnetting. It allows us to group multiple network addresses into one network address to minimize the weight in the routing table. So what we could do is we could actually group these network addresses together. So it would cut down on the amount of routes in a routing table. So we could group all these together to make them look like one network instead of 4 different networks. Or in some cases, instead of 100+ different networks, we can group them together. Now the key thing with CIDR is we have to have, if we're going to group these network addresses together, we have to have the appropriate network addresses to do that. They have to be in succession, and they have to start and stop with a certain particular address. They're going to be in groups of 2s. Group of 2 to 4, 8, you're going to have the appropriate number of addresses. And all I'm going to do is I'm going to make these look like one network address. I have 4, 5, 6, and 7. 200.100.4.5.6, and 7. And all I have to do is change the subnet mask. And what I do is I change it to the point where they all look the same. I've converted into binary here. 200, 100, and then I converted the 4 to binary, the 5, the 6, and the 7. And all I have to do to supernet these is say, okay, at what point do they stop looking the same? They all look the same, they all look the same. They all have a 1 in this spot right here. They all have 1s. They don't all have the same values here. So what I do is I draw the line where they stop looking all the same. And then to the right of the line, I need to make sure I own every different combination that's possible for the 0s and 1s here. I own 0, 0, 0, 1, 1, 0, and 1, 1. So that's all the combinations. So I can supernet this. And all I have to do this is change these values into a 0. So by grouping these together, 200.100. This value is 4. 4.0 with a new subnet mask of 255.255.252.0. All those networks look the same. Or CIDR notation, which would be 22/22. This is called CIDR notation. But just because you see this, I like to call it bitwise notation. Just because I see something like that doesn't mean it's CIDR. If I had a class A network address, like our 12, something like this, and a /22, that's not CIDR because that's a subnetted class A. CIDR is taking multiple network addresses and grouping them together like I did here, and this is called CIDR notation, but it's also called bitwise notation. So again, all I have to do is line them up, dial the subnet mask back instead of moving it forward like we do in subnetting until they all look the same, and make sure I have all the combinations of 0s and 1s possible, and that's supernetting, also known as CIDR. 200.100.4.0, and then this new subnet mask of 255.255.252.0. Now let's take a look at what's called variable length subnet masks. We're going to take the 12.80 subnet and break it down further. What might happen is you might have a subnet coming off of a router 12.80.0.0, and you might need to break it down even further into multiple additional subnets. So let's say we were going to use VLANs and chop this one subnet up into 75 additional subnets. So here's our starting point. So what this happens is the rest of the network will be using a /12. This part of the network will be using something different. So all we have to do is same thing with normal subnetting. Figure out how many binary spaces we need to get 75 combinations of zeros and ones. And how I do that is I just start multiplying some 2's out. And it takes 7 additional 2's, or 7 binary spaces. So I turn the next 7 bits on. So what that gives me is a new subnet mask. Everywhere else in the network's using /12. Here it's /19. So our new subnet is going to be something like this. So it'll be 12.80. This value is 32.0 is our first subnet. 1280.64.0. This is going to go in increments of 32 here. 96. 128. And I can keep going. I just keep adding 32's. Eventually, when I use up all these combinations, it'd be 12.81.32.0, and I'd go back and forth. So this is variable length subnet mask. I use a different subnet mask in one subnet that I use in another subnet or throughout the rest of the network. Not all routing protocols will support this. We'll talk about that in the routing protocol section. So we have talked about subnetting, why we subnet, binary subnetting, we did a practice problem with that. CIDR, also known as supernetting and CIDR notation, something like that. Variable length subnet masks, and again, here's a couple of references for some practice. Learn to subnet.com and subnettingquestions.com.